The third thing about tension is that consideration that we have a simplification of these problems here is that when we have a rope in all these problems, the rope is always going to be massless. And whenever we have pulleys in problems, the pulleys are always going to be massless too. Now this is very unrealistic, but it's just an approximation of the problem that maybe doesn't work out to be too bad in a lot of cases, because you consider, like, if you have two heavy bricks or something like this that you connected to a rope, maybe these bricks are really heavy and the mass is very light compared to the mass of either of the bricks, and so it would almost be like the rope is massless here. And likewise, if say you had a pulley like this that was made out of maybe some very light but durable plastic or something, and you had a couple masses hanging over it like this here, you have this light rope in here, at least light relative to the mass of the two bricks here, these two heavy bricks, and maybe even the bricks and all these things are even very heavy compared to the plastic, the thin plastic that the pulley is made out of, so you have a massless pulley as well. Now, in the case where the rope and the pulleys are massless, which most of these problems are going to be like, you will be told very in particular, if this is not the case here, we have sort of another idea about tensions here, is that T in a given rope will be the same throughout. T in a given rope will be the same throughout. So if you have a rope, say here's a ground here, and here's a block here, and here's a block here, and you have a rope connecting them like this, tensions always pull away from the points of contact, and so you would definitely label this like T, and you can definitely label this T as well, but you would not label this T1 and that T2. You don't have to go through any special consideration to say maybe the tension on one end of the rope is different than the other tension on the other end of the rope. No, you don't have to do that, because we're saying that in the case here where the rope and the pulley are both massless, T in a given rope is the same throughout. So you would not label this T1 and T2. In fact, you just get rid of the T1 and get rid of the T2, and it's just going to be a T throughout. That's it. Same thing would apply to the Atwood machine over here. Here's the same light rope going over the same light or massless pulley here. There will be a T pulling up that way, because tensions always pull away from the points of contact. There'll be a T up there and too, but you would not label this T1 and T2. That would not be correct to do that, because it's the same rope. The same rope always has the same tension throughout, so there'll definitely be a T1 here, and if you wanted to call that T1, you'd call this T1, or since it's the same rope, just dispense with the subscripts altogether and just call that T and that T as well. As long as it's the same T, then you are correct, because T in a given rope is always the same. And the last point about tension, point number 4, is as follows here. Is that objects linked by a rope have the same V and A. Objects linked by a rope will always have the same velocity or speed and the same acceleration. They have to. Here's just a couple of examples to draw. Let's go back to the Atwood machine, which looks like this, and it looks like this. Here's a rope going over the Atwood machine. Now, a couple things, the speed and the acceleration. Well, let's just look at it this way, maybe just use a little bit of common sense here. Suppose this block was going down with a speed V maybe of 5 meters per second. The question is, what is this other block going to do? Well, they're connected by a rope over the pulley, and the rope is always going to stay nice and tight. So if this block goes down at 5 meters per second, this one must go up at 5 meters per second. There's just no other way about it. If this one started to go up at 10 meters per second, it would go up twice as fast as this one's going down. The rope would start to bunch off, likely come off the pulley. You have a big disaster. Likewise, if this one's going down at 5 meters per second, this one started going up at 1 meter per second, this one would be trying to go down faster than this one's going up, and eventually you're going to stretch and break the rope, so you can't have that either. So just looking at it sort of empirically like that, you can probably agree then that objects linked by the rope have the same V. They just have to. That's just the way it's going to go to keep the rope nice and tight and prevent it from breaking and so on. The acceleration may be a little less obvious, but it's sort of the same type of argument here. Suppose this one had some downwards acceleration here of 4 meters per second squared. I don't know where that number came from, but it is. Just say it's going down 4 meters per second squared. It's the same sort of consideration as velocity, that if this one is going down at 4 meters per second squared, that means every second it's picking up another 4 meters per second of velocity, say. That's one way of thinking about it. And so if this one is going to pick up velocity at that rate, this block must do the same thing. this one can't, if this one's accelerating at 4 meters per second downwards, this one can't, for instance, say be accelerating upwards at 1 meter per second. That way at different times they're going to have different speeds, and that sort of violates our first idea that the v has to be the same for both of these things. Likewise, if this one's going down at 4 meters per second, this one cannot be going up, say, at 1 meter per second. This one is going to pick up speed at 4 times this one's 1 meter per second, so eventually this one's going to be going faster than this one, and again, we're in the situation where the rope could break or some disaster could happen, so that doesn't happen either. So just sort of remember that as you work through these problems, that when objects are linked by the rope, they have the same speed and they have the same A. It's just common sense, and it's just the way things must behave if we want the system to stay properly attached, the rope to stay nice and tight, and for nothing to fall apart.